So we're going to be talking about applications of thermodynamics. Keep in mind, we started thermodynamics all the way back in Unit 5 when we talked about delta H and heat and energy changes and calorimetry. Well, there's a bit more to it than that as far as how reactions happen. So we're going to be talking about entropy first. And we had enthalpy, which was delta H. Entropy is S. And entropy is commonly defined as a measure of disorder in a system, but that's not necessarily the best way to define it. That's just, I guess, a everyday definition of it, but it's not specifically accurate or precise. So to be more precise, it's a measure of how much energy is dispersed in a system. So if energy is more spread out in a system, that's higher entropy. And that brings us to what's called the second law of thermodynamics, which says the entropy of the universe is constantly increasing. And anytime a chemical reaction takes place, the entropy of the universe goes up. And then you have the third law of thermodynamics, which says as temperature approaches 0 kelvins, entropy approaches 0. And more specifically, what it says is the entropy of a pure crystalline solid at 0 kelvins is 0. You may also be wondering, well, what's the first law of thermodynamics? Well, the first law of thermodynamics is the law of conservation of energy. And then there's also the 0th law of thermodynamics, which says this. You don't need to worry about it. But basically, that just says that thermometers work. So just to kind of look at it this way, if energy is like money, spreading around the money is increasing energy dispersal. So the more you spread energy around, entropy goes up. Now, generally speaking, there are 5 ways that entropy can be increased. The first is you change state, going from solid to liquid, or liquid to gas, or gas to plasma, or solid to gas, or liquid directly to plasma. Anytime you're moving from the more confined states of matter to the more dispersed states of matter, entropy increases. So for instance, if an ice cube melts, entropy has gone up. Right? That also kind of explains why ice cubes actually do melt, because energy is actually going that's an endothermic process. It's absorbing energy, but yet it still happens. We'll get to that tomorrow, but it's pretty cool stuff. If you release a gas from solution, entropy goes up. For instance, if you open up a carbonated beverage and the carbon dioxide starts coming out of it, that's increasing entropy. Or if you do a chemical reaction that forms a gas, entropy goes up. Which goes right into number 3. If a chemical reaction produces more gas particles as products than it does as reactants, entropy goes up. And I can show you an example of that. If we consider the combustion of butane, C4H10, that produces carbon dioxide, gas, and water vapor. And it uses oxygen gas. And when we balance this, we end up with so even if our butane starts as a gas, we have 15 gas molecules here. We have 18 gas molecules here. So we can say our change in entropy is positive. Entropy went up because we went from 15 gas molecules to 18 gas molecules. We have taken the energy that was confined in these 15 gas molecules over here on the left side, and we've turned it into 18 gas molecules that are more spread out on the right side. The fourth thing we can do is you can dissolve a solid or a liquid into water. So for instance, if you have an ice cube and you have water, as that ice cube melts and it essentially mixes with it, that increases entropy. If you dissolve salt into water, entropy increases because the energy that was confined in the sodium chloride crystal is now more dispersed throughout the solution of salt water. And fifth, anytime the temperature goes up, entropy goes up. So just to kind of put a final note on this part for today, all chemical systems want to go to the lowest energy level or a lower delta H, and they also want to move towards higher entropy. These are the two things that actually drive chemical reactions to happen, is releasing energy, being exothermic, and increasing entropy. So if you have a reaction that is exothermic and increases entropy, such as the combustion of butane, this is a reaction where delta H is negative, then that reaction is going to be favored to happen under every possible condition. And the reverse of that reaction, carbon dioxide and water combining together to make butane and oxygen, is never going to be favorable. So you're not just going to have the carbon dioxide and water vapor molecules here in my office combining to make oxygen and butane. If they did, that'd be pretty cool. We could essentially make fuel for free, but that's just not going to happen because it's essentially violating the laws of thermodynamics, right? So at this point, I'm going to provide you a link to a crash course chemistry video where Hank Green also talks about entropy, so you can get a different perspective on entropy if you want. And then I'm going to post a little assignment where you try to identify which things have more or less entropy. So hope y'all enjoy this little lesson for today.